Continuing earlier some examples on Thevenin's theorem. Now we can take one more example with respect to the dependent voltage source. So consider this circuit. It has a one independent source and one dependent voltage source. So this circuit we have to replace with the Thevenin's equivalent. Thevenin's are Norton equivalent with respect to terminals AB. With respect to terminals AB, it has 3 resistors here and one current. I1 is the current. The amount of current I1, so which will be related to the voltage source 2I1. This is the dependent current source. Sorry, dependent voltage source. 20 volts. Now how to determine the Thevenin's equivalent and Norton's equivalent. First step, coming to the first step, we have to determine the voltage across these two terminals AB. That is nothing but a drop across this 6 ohms because no current is flowing in this 10 ohm. So I have to determine the drop across this current, drop across this 6 ohm resistors. So now just I am called it as a one mesh here, one mesh that I. So I is nothing but a I1 also. Both are same here. I and I1 are both are same. Here anyway no current flows, only one mesh is there. Now I will write a mesh equation for this I. 6I minus 2I, this is the source here. Again 6I or I1, both are same, minus 20 is equal to 0. And 6I, okay. Because this is 6I and minus 2I, we can make it as a minus 20 when we taken it. 12 and minus 2 to the 10I, I is equal to 2 ampere. I is nothing but a I1. Then voltage across this is VOC, simply 6 into I1 or 6 into I, it is a 12 volts. So we determine the voltage across these 2 points. So VAB is also equal to VOC or also equal to the drop across 6 ohm. Next step is the determining the Thevenin's equivalent. Whenever to determine the Thevenin's resistance, when dependent current source or voltage source appears in the circuit, we have to short circuit the terminals AB. So we have to determine this ISC. First step is determine the IS here. So when I short circuited here AB, when I short circuited AB, which is ISC, here there are 2 mesh here. One you will call it as X, another one you will call as a Y. When we solved for Y, that is nothing but a short circuit current here, and that is a no. Now come to this mesh here, and this is I1 here, and the direction of X and I1 are same, but Y is opposite to that. Means X minus Y is nothing but I1 here. X minus Y is I1 here, the current that I1. So for this KVL first mesh equation, 6 plus 6, 12x minus 2I1 minus 6y, because opposite here, then minus 20. 12x minus 2, I1 is x minus y, minus 6y is equal to 20. 10x minus 4y is equal to 20. Then 6x minus 16y is equal to 0. Here, okay, when coming to this second mesh y, okay, KVL for this is 10 plus, it is a 16, okay, you can call it as a 16. 6x, because with this, both current x and y are flowing here. Yeah, minus 6x here, because opposite here, plus 10 plus 6, it is a 16y. No voltage source here, 0. Or we can rewriting this 6x minus 16y. So the first equation is 10x minus 4y is equal to 20. Second equation, this one, by solving these two simultaneous equation, x is equal to 2.3 and y. So y is nothing but a ISC short circuit current. Then R Thevenin, it is nothing but a V Thevenin ISC. It is a 12 volts, what we determined here earlier, and this 13.6 ohms. And equivalent circuit is 12 volt in series with the R. It is a current source. In terms of an Norton, replace this voltage source into a current source. So 12 divided by 13.6 is a current, and this resistance will come into the parallel.